All right, so we got sets today. This will be section 2.1 out of the book. And let's go ahead and just jump right into probably the most complicated definition that you'll see in the entire course. No, I'm kidding. A set is just a collection of objects. It's very straightforward. It really is just what you would think of in real world as a set. You know, I've got a set of things. I'm holding them all in a bag. That's my set. Boom. A fairly straightforward definition. Let's look at some examples here. So if I take all the letters in the alphabet, that's a set, right? A, B, C, D, E, F, G, all the way down to Z. Though that's a collection of objects. And even better, we can assign a name to it, right? All of the letters in the alphabet are just the alphabet, right? Um, let's look as well. Tall people in this class. So, you know, we've got our whole class. We've got a bunch of different people in it. Everybody's different heights. I say tall people. Now, here's a question to think about, and I'll get to this a little bit later, but what do I mean by tall, right? Everybody might have a different definition of what they think tall is. Do I just mean people taller than you? Do I mean people that are over 6 feet? You know, what do I actually mean by that? And I'll let you kind of mull on that for a little bit. We'll get to that in a second. Now, contrast that with people over 6 feet tall. Think about that as a set. That's a collection of people, right? And I would argue that we actually know exactly what that is, right? Months that begin with the letter M, that's a set. That's a little bit harder to sort of assign a name to it like we did on the alphabet, right? When I talked about A, B, C, D, E, F, G, and so on, I could just say, hey, this is the alphabet, right? But down here on months that begin with the letter M, there's not a predefined name for that. So what we can do is we can actually just give it a name. And what I'm going to do is I'm going to give it this sort of script M, this fancy capital M here. And notationally, what we do is we say, okay, this fancy capital M, that's my name for this set of months that begin with the letter M. And that's equal to the set of, when I say these curly braces, that's me saying, hey, it's a set of all these things. It's a collection of all these objects. March and May, those are the months that begin with the letter M. So March and May, sort of enclosed by these brackets, that gives me the set that I'm going to call this script M, this capital M, which stands for the months that begin with the letter M. We'll do a bunch more examples so you guys will see more about what I'm talking about. So let's look here at some little comments on sets, and we're going to start off with this idea of a set being well defined. Okay, so what I mean here is a set is well defined if I can take an object, take something, and place it in the set or not place it in the set. If I definitively know whether or not it can be in that set, that tells me whether or not it's well defined. So let's come back over here. Let's take a look at tall people in this class and people over 6 feet tall in this class. Let's actually copy this on over here. So I've got these two sets here, and could anybody tell me if they're well defined or not? To me, I think that tall people in this class is not well defined. I'll just do WD just for an abbreviation. Because, and the reason I think that that's not well defined is because, again, this definition of tall is subjective. There's nothing there that tells me that I can definitively be placed in it. There could be someone who's 6'5", but maybe they're not considered tall if they're standing around a group of people that are all 7 feet. And so maybe they're not even in that set of tall people in this class. It really just depends. And so we'd say that set is not well defined because I can't objectively place people in it or not. They might be in it, they might not. It really just depends on the context. However, people over 6 feet tall, that is a well-defined set because you are either over 6 feet tall or you're not. And if you are, then you're in this set. If you're not, then you're not in the set. So that's me objectively placing each person in the set or out of the set. So that means that that set is well defined. Okay. Now, I've been using this sort of phrase, object or oh, you got a person is in this set. A lot easier and a more mathematical way of describing the things that are in a set is to use the word element. Some people use member, but I generally like to use element. Kind of depends on the context. But if I have a set, let's just say I had a set of numbers. I'm going to call the set A. And it's the set of numbers 1, 2, 3, 4, and 5. Each of these numbers, 1, 2, 3, 4, and 5, those are each elements of the set. So I might say that this set has 5 elements in it. I could say, oh, all of the elements in this set are numbers. Versus back here, the elements of this set M that we talked about, the elements are March and they're May. So this word element just gives us a way of describing an object in the set. It really means the same thing as object. We just don't like to use the word object mathematically. So let's go ahead and look at some common sets, some sets that you'll see. And again, I'm using this notation here with these script sort of letters, or these, italicized letters, and these curly braces and these equal signs. So I'll sort of keep mentioning that as I give you more and more examples of sets. You'll get to the point where you'll see so many of these that you'll start to get the hang of it. But for now, let's take a look at the natural numbers, and this is just a name of the set of just all whole numbers. Okay, so you could probably see this pattern. You could use inductive reasoning like we talked about in the last lecture. And you could see that the numbers here are just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're going to keep going on. They go on forever. And if you take that set of numbers, that's what we call the natural numbers. Okay. So again, just talking about this notation, I say N and this is just a capital italicized N. That is the name of my set. And I'm saying that that is equal to the collection of elements inside these curly braces. And all of those elements are just the numbers 1, 2, 3, 4, 5, 6, 7, 8, and so on and so forth. So that's sort of notationally what's going on here. Let me be very clear. If I write the set 1, 2, 3, 5, 6, 7, 8, 9, and then I keep going on, that is not the natural numbers because it doesn't include 4, right? There's a 4 missing right there. So this is a set of numbers, but it's not the natural numbers. We reserve the definition of natural numbers solely for just this set exactly. Okay. Or sort of similar to the natural numbers, we have the even natural numbers, and just as you might expect, it's all of those natural numbers that we had up here, but they're just the even ones, 2, 4, 6, 8, 10, 12, so on and so forth. We will denote that with an E generally. You also could have O, the odd numbers. A lot of times this isn't denoted with an O, it's denoted by just something else. I'll just call it an O for now, that's okay. And so that's all the odd natural numbers. Sometimes people just say the naturals. They'll say it's the odd naturals. And last of the sort of common sets that we'll see is the empty set, sometimes called the null set. And we give it two different we give it a notation. We give it this circle with a line through it. And again, that's the name. Just like N was my name for this set of natural numbers, E was my name for the even natural numbers, O was my name for the odd natural numbers. This symbol is the name for the empty set. And the empty set here is just a collection of nothing. There's nothing in it, right? So here's a trick question. Let's say I give you a set. Oh, let me keep that there. say I give you a set that looks like this. So let's call this B. I'm just going to give it a name, B. Is this set empty or is it not empty? And at first you look at this and you're like, well, yeah, hey, look, there's nothing in it, right? So it must be empty. But if you look very carefully, this set here, use a different color. This set here, the outer braces here are what define my set. And inside those braces, there's something in it. Now, granted, that something is a quote unquote nothing, but inside these braces that I'm pointing to in the green, there's something in that, in between there. So this set B is not an empty set. So you want to be careful there. It's a little weird to say that, oh yeah, it has something in it, but that something is nothing. It's a little weird, but it's true. I mean, the thing that's inside this outer set here is nothing, which means that that something is in it. This is very different from writing, let's call another set C. It's very different from writing this. This is a set that has absolutely nothing in it. There's no sets inside of it or anything like that. You want to be a little bit careful there. So let's look at some notation on sets. I've been using a little bit of notation already. So what I could say is, let's say that I have a set, and I'm going to give it a name. I'm going to call it A right here. And that is the set of, again, these curly braces, that kind of means the set of everything inside of them. It's the set of states that border the Pacific Ocean. And you can probably, if you grew up in California or like I did, or in Washington, Oregon, or somewhere close by, hopefully you know that these states are Washington, Oregon, and California. So that's the set there, and I could do this. I could put an equal sign, and I could put some curly braces around it. Those are the three elements in my set. And I want to use that word element very carefully here, because I'm now going to call out to the element that's Oregon, right? And if I want to say, hey, Oregon is in this set, maybe someone didn't know which states border the Pacific Ocean, and you wanted to tell them that Oregon was a state that bordered the Pacific Ocean. What you could say is that Oregon is in A. So this little weird E looking thing, that means is an element of, or it's in A. So this right here that I've boxed, if I read that out verbally, I would say Oregon is an element of the set A. And I know that A is the set of states that border the Pacific Ocean. So this right here tells me that Oregon borders the Pacific Ocean. It might seem a little roundabout to do that, but it's sort of the mathematical way of saying, hey, Oregon is an element of this set A that I'm talking about. I could go the other way with this. I could say, hey, the set R contains the elements 2, 4, and 6. And there's a handful of ways that you could write this out. You could just go really, really straightforward, and you could say, hey, R, well, it's a set that has 2, 4, and 6 in it. So it has 2, 4, and 6. You could write this a little bit more mathematically, and I'm gonna go very slowly as I read through this. This guy down here on the bottom. R is the set of things that I'm going to give them a label as X. So I'm going to label these things as X, and it's any X such that X is an element of the even natural numbers and X is less than 7. Now that's a mouthful, but it's about as precise as you could get when I talk about the set containing the elements 2, 4, and 6. Again, let me just go back through that. The set R is all of these numbers that are even and less than 7. Well, that's 2, 4, and 6. Those are the even numbers that are less than 7. And so while this does seem kind of convoluted, this can get very, very helpful. Because what if I was talking about a set, what if instead of 47, or instead of 7, I made this 47, right? You don't want to write out every single even number less than 47, 2, 4, 6, 8, all the way up to 42, 44, 46. That's just way too much writing. So this is a much cleaner way of writing that. Let's actually just do an example there. So let me give myself a new page here. So if I said that the set M is every odd number less than 100. So at this point, you could, if you really wanted to, you could say that M is equal to the set, and it would be all these odd numbers less than 100. So 1, 3, 5, 7, 9, 11, and you could keep on going. But I don't want to do that, because that's just going to take me a long time to continue writing. And I also want to be careful, because if I box my answer as something like this, these ... dots are implying that this thing goes on forever, and it doesn't, because I have to be less than 100. Right? So this right here is really just, this is bad. Don't do that. It would be a lot cleaner to write the following. M is the set of things that I'm going to give them a temporary name. I'm going to call it X, such that, that's what this bar means. It means such that X is an odd. Remember, we use that O. Let's just say odd. I use that symbol O before, but I don't want to confuse it with a 0, so I'll just write odd. X is an element of the odd natural numbers, and X is less than 100. And finish off with those braces. What I'm saying here is that this set M is everything. It's all of these elements. It's this collection of objects. And each element, I'm going to just kind of call it X temporarily. And X has to be odd, and it has to be less than 100. That gives me 1, 3, 5, 7, 9, 11, 13, all the way up to 95, 97, 99. And then we would stop, because any more we go greater than 100. And we don't want that. So here's this sort of an example of how I can use this notation to talk about very large sets a little bit easier. Let's go ahead and look at a definition. You won't hear me talk about this too often, but it pops up enough that it's worth talking about it. The definition of cardinality, and it's very simple. It's just the number of elements that are in a set. So if I give you a set here, let's call it T is equal to dog 3, B, lowercase b, fish, I don't know. I'm just, Oregon, let's do that. I'm just coming up with random things. This is a set. This is a collection of objects. Granted, they're not really that related to each other, but it's a collection of objects. And if I ask myself how many things are in this, I'd say there's 1, 2, 3, 4, 5, 6. There's 6 things in this. There's 6 elements. So the cardinality would be 6 here. That'd be my cardinality of this set. Now, let's go back to the natural numbers. Again, typically denoted by n. You're welcome to denote it with something else, but if you write n, I'll know that you're talking about natural numbers. This is 1, 2, 3, 4, and it keeps going on forever. So there's an infinite number of things in this set. So we would say the cardinality is infinity. I'll circle that. There's very interesting stuff that you can get into with cardinality and infinity, and there being different levels of infinity. I kind of just say that to make you go, ooh, that's weird. Different levels of infinity. It just kind of sounds cool. I'm not going to get into any of that, but there's some really cool stuff there if anyone's ever interested. All right, let's continue on. We've got cardinality defined. We've seen some examples. We also have this definition of finite and infinite sets. So a set is finite if its cardinality is a natural number. And that's just a fancy way of saying, well, if the cardinality is just a number, right? If it's a number that I can write down, it's 17 or something like that. If the number of elements in a set is a natural number, the set is called finite, right? So this example back here with the 6 elements, that set is finite. A set is infinite if it's not finite, which is, again, just sort of a roundabout way of saying if there's an infinite number of things in it, the set is infinite. The natural numbers are infinite there, because there's an infinite number of things there. Here's a question. What would this set be? Would it be finite or would it be infinite? Let's say the set S equals all possible paintings. So this is the set of all possible paintings that could ever be painted by anyone in the world. Is that infinite or is it finite? I would personally say it's infinite, because if you've got, a canvas and you're filling it with paint, there's an infinite number of colors that you could choose from. And so right there, you could just have someone paint the canvas, with all blue, and then someone else could paint it with all red, and then someone else could paint it with all green. And you've got an infinite number of shades there. You've got all sorts of colors that you could use. So this would be an infinite set, I would say. Great. Let's keep moving on. Some more definitions of sets. This one is always tricky. This actually still trips me up. I still sometimes accidentally flip these definitions. So let's be careful here. We're going to talk about sets being equal and sets being equivalent. They seem like they should mean the exact same thing. They don't. There's reasons for it. I'm not going to get into those reasons. But if we say two sets are equal, that just means they're the exact same thing. Written down, word for word, letter for letter, they're the exact same thing. That means that they're equal. Two sets are equivalent if they have the same number of elements. And this is where things get a little weird. If I have a set A and I have a set B, and the set A is dog, 2, cat. And this set B is fish. Well, here, let's do this. I'll make it even more different. 4, fish, 12. I don't know. These sets, as weird as it may sound, these sets are equivalent. They're not equal, but they are equivalent. And they're equivalent because they have the same number of elements. And you might be sitting here thinking, why would you use this word equivalent? Why not use something else, similar or something like that? It seems like this use of the word equivalent is poor. And what it really comes down to, it comes down to this idea, excuse me, I skipped over that, of infinite sets. And you can have a whole lot of different types of infinite sets. You can have the natural numbers. You could have the even natural numbers. Those are both infinite sets. You can start asking yourself, do they have the same number of elements in them? Even though there's an infinite number of elements. Remember, I kind of talked about those levels of infinity. That's where things get really weird. I could talk for days on all this stuff, but I don't want to confuse you guys. For now, just stick with these definitions of equal and equivalent. Bear with me, and then being weird, just know them, because I'll ask you about them. Great. What we've got here, similar to equal and equivalent, actually I should say similar to equivalent, is that two sets have a one-to-one correspondence if each element can be paired with another element, and vice versa. So in these sets here, I could pair dog with 4. I could pair 2 with fish. I could pair cat with 12. And what I've done there is I've paired each element up with each other. And let me say that again, that sounded bad. I can pair each element in A with a specific element in B, and vice versa. I can pair each element with B with a specific element of A. And that means not only are they equivalent, but they have a one-to-one correspondence, because I can pair each thing with exactly one other. So if I give you an example of two sets here, let's say set C equals 1, 2, 3, 4. Set D is A, B, C, D. These have a one-to-one correspondence. I can just pair these straight up with each other. 1 to A, 2 to B, 3 to C, 4 to D. Heck, even if I wanted to, I could do something weird like this. I could pair them up that way. I'm still pairing them. That means that there's a one-to-one correspondence here. But now let's say I do this. Let's say I add E here. There's a different number of items. There's a different number of elements in these sets. They have different cardinalities. So I can't pair these as much as I might try to. I can't pair everything with everything. This E is sitting there all alone, right? And then even if I go like this, if I go the other way, I could pair E to 4, I could pair D to 1, I could pair C to 2, I could pair, C to 3 and B to 2. But this A doesn't have anything left to pair with. So these would not be in one-to-one correspondence with each other. So we've got that definition there, which you could probably tell, and I'll leave this for you guys to kind of think about. There's obviously a very, very, very close relationship with sets being equivalent and sets having a one-to-one correspondence. They actually mean the same thing. So that's going to be it on sets. I know there's a lot of notation here that we're talking about. You know, like I've said, you're going to see this type of notation over and over and over and over. So I'm hoping just to kind of throw you in the deep end there, let you just be, you know, hit in the face with this notation over and over, and you'll start to get the hang of it. This is definitely something to you know, watch several times, make sure you got it, make sure you understand these sets. One thing I do want to mention, I've kind of alluded to this, but I want to outright mention it before I leave. When we use N or E or this empty set notation, we generally mean the natural numbers or even natural numbers, like for N and E. We don't like to use those letters N and E to call sets other things. Like you'll notice I've used B, I've used C, I used A here, I used R. We generally don't like to use N and E for sets that aren't the natural numbers or the even natural numbers. And that's what I'll just leave it with. And hopefully this all made sense, and I'll see you guys next lecture.